Hello everybody, welcome back to my channel. Today we will discuss an important spectroscopy, organic spectroscopy, infrared spectroscopy. We had already discussed the UV visible spectroscopy and its applications. Here we will discuss different aspects of infrared spectroscopy, such as what happens when molecules absorbs infrared radiation, what are the different types of or modes of vibration or fundamental vibrations, what are the factors which complicates the IR spectrum, and how is the vibrational frequency is calculated using Hooke's law, and how is the IR spectrum used to determine functional group and the molecular structure of organic molecules, etc. Okay. See, almost any compounds having covalent bonds absorbs various frequencies of electromagnetic radiations in the infrared region of electromagnetic spectrum. Any organic compounds having covalent bonds absorbs various frequencies in the infrared region of electromagnetic spectrum, right? Among the infrared region, vibrational infrared portion 4000 centimeter inverse to 667 centimeter inverse is of greatest practical use to organic chemists, right? See, the region 12,500 centimeter inverse to 4000 centimeter inverse is called the near infrared region, and the region 67 to 50 centimeter inverse is the far infrared region. We are concerned 4000 centimeter inverse to 667 centimeter inverse region in the determination of vibrational frequency of organic compounds. Okay, you know, the absorption of infrared radiation by molecules occurs due to quantized vibrational and rotational energy changes when it is subjected to infrared radiation. That is, when a molecule is exposed to infrared radiation, both the vibrational and rotational energy transitions takes place, and hence IR spectra are often called as vibrational-rotational spectra. Vibrational-rotational spectra. That is, vibrational transition is also associated with rotational transition, because within the electronic level there will be vibrational levels and rotational levels of closed or very close energy spacing, and hence when infrared radiation absorbs, the energy changes from rotational levels also taking place along with vibrational levels, and hence the spectra obtained is a vibrational rotational spectrum. Okay, see, unlike UV spectra which have relatively few absorption bands, IR spectra have a large number of absorption bands. IR spectra have a large number of absorption bands compared to UV spectra, and therefore provide plenty of structural information about a molecule compared to UV spectra. Okay, here different bands observed in IR spectrum corresponds to various functional groups and bonds present in the molecule. Thus, IR spectra is most widely used for the detection of functional group and the identification of organic compounds. Okay, then see how is the infrared spectrum is used to get the structural information of organic molecules. Since every type of bond has a different natural frequency of vibration, and since of the same type of bonds in two different compounds are in two slightly different environments, same type of bonds in two different compounds may have slightly different environments, and hence no two molecules of different structures have the same infrared absorption pattern or infrared spectrum. And so we can say different molecules will have different patterns of infrared spectrum, because every type of bond has a different natural frequency of vibration, and even though if the different compounds will have the same type of bonds, but they may exist in two slightly different environments, and hence no two molecules of different structures will have the same infrared absorption pattern. Okay, thus the infrared spectrum can be used for molecules much as fingerprint can be used for humans. By comparing the IR spectra of two substances thought to be identical, you can establish whether they are in fact identical. Also, if their IR spectra coincide peak for peak or absorption for absorption, in most cases the two substances will be identical. That is how we will determine or we will identify the organic compounds using IR spectra. That is, we have to compare peak for peak or absorption for absorption in two compounds, and if these peaks are same or absorptions are same in both the compounds, we can say the two substances will be identical. Okay, that is how we can identify molecules with IR spectrum, right? The second and more important use of infrared spectrum is to determine the functional groups present in a molecule. That is one of the important use of infrared spectrum. That is, infrared spectrum is used to determine the functional group. For example, the absorption of each type of bond, such as NH, N single bond H bond, C single bond H bond, O single bond H bond, C single bond X, X is halogen, C double bond O, C single bond O, C single bond C, C double bond C, C triple bond C, C triple bond N. These are all functional groups and so on, are regularly found only in small portion of vibrational region or IR region. Each of these groups are usually found in the vibrational portion, small portion, vibrational portion of IR region. Small vibrational or frequency portions in vibrational IR region. For example, CH. Usually CH stretch is usually found in 3000 plus or minus 150 centimeter inverse. That is the small portion. It may be 3150 or maybe 2850, and this you can see the CH absorption or stretching absorption will take place in this small portion of frequency in IR region. Similarly, C double bond O usually absorbs 1715 plus or minus 100 centimeter inverse. That means it is the portion where this C double bond O absorbs in different molecules. Okay, and so each of these functional groups will absorb a small portion of IR region, and hence we can examine whether there is any peak in this region and found the molecule will have that function group present. Okay, that is the method. Okay, see in this chart you can see the approximate range of absorption of each of these function groups. For example, you can see the C double bond O function group, C double bond O function group absorbs in the range around 1675 to about 1880 centimeter inverse. Similarly, you can see the C double bond C stretch and C double bond N stretch is usually taking place in the absorption range of around 1600 to 1680 centimeter inverse. Similarly, you can see the OH stretch and NH stretch usually taking place in between 3100 to 3700. Usually OH stretch takes place between 3200 to 3600 centimeter inverse, and you can see the CH stretch usually taking place in between 2800 to 3000 about 3200 centimeter inverse. The CH bond stretch takes place, and so we can say you can by seeing this chart, each of these function group absorbs frequency within a small range, within small ranges, and hence by examining the peak, by finding the peaks in IR spectra in these ranges, we can find the function group present in the molecule. That is the way how the function group is determined by using IR spectroscopy, right? You know what happens when infrared radiation is absorbed by a molecule. See, infrared radiation is absorbed when oscillating dipole moment due to a molecular vibration interact with the oscillating electric field of the infrared beam. That is, infrared radiation is usually absorbed when the oscillating dipole moment of the or due to the molecular absorption interact with the oscillating electric field of the infrared beam. Okay, that means the infrared absorption takes place only when the oscillating dipole moment created by the molecules due to the molecular vibration interact with the oscillating electric field of the infrared beam. When these two factors interact, then the infrared radiation is absorbed by the molecule. Okay, that is, an absorption band appears only when a molecular vibration produces a change in the dipole moment of the molecule. Okay, otherwise the vibration is said to be infrared inactive, and will show no absorption band in the infrared spectrum. See, it is not necessary for a molecule to have a permanent dipole moment for IR absorption, but molecular vibration should lead to dipole moment change. That is the minimum condition for IR absorption. Okay. Usually, larger the change in dipole moment, the higher is the intensity of absorption. Okay. Now let us consider the different modes of vibration within the molecule undergoing after the absorption of IR radiation. See, various atoms in a molecule may be regarded as balls. Various atoms in a molecule may be regarded as balls of different masses, and the covalent bond between them as weightless tiny springs holding such balls together. You can see these are two atoms which are holding by a weightless spring, and these atoms are usually regarded as balls which are connected by a weightless tiny spring, and this weightless tiny spring can be considered as a covalent bond which connected these two atoms within the molecule. Also, you know, atoms in a molecule are not still, but they vibrate. Atoms in a molecule are usually vibrate. The two types of fundamental molecular vibrations are stretching and bending vibrations. Stretching and bending vibrations are two fundamental modes of vibration undergoing these atoms which are regarded as balls connected with a weightless spring, and the spring is regarded as covalent bond, and so such a system may vibrate either by stretching or by bending, right? In stretching vibration, the distance between the two atoms increases or decreases, but the atoms remain in the same bond axis. Such vibrations are of two types, the symmetrical stretching and asymmetrical stretching. That is, in stretching vibration, the distance between the two atoms increases or decreases, but the atom remains in the same bond axis. You can see the symmetrical stretching of CH2 group. Here, these atoms, carbon atom stretch, the hydrogen atom stretch through the carbon-hydrogen axis. The distance between these two atoms, carbon and hydrogen, may increase or decrease because of the stretching, but the atom remain in the same bond axis, carbon-hydrogen axis, carbon-hydrogen axis. Stretching, that is, the distance between these atoms increases or decreases, but the atoms remain in the same bond axis. Okay, it is symmetric stretching. In symmetric stretching, the movement of atom with respect to the common atom, here the carbon atom or the central atom, is simultaneously in the same direction along the same bond axis, in the same direction here, same direction in the same bond axis. It is symmetrical stretching. And in the asymmetrical stretching, one atom approach common atom while the other depart from. It is this carbon-hydrogen, this hydrogen depart from this common atom, carbon, and this hydrogen approaches the common atom, carbon, and so one stretches towards or away from this central carbon atom, and this hydrogen atom approaches the central carbon atom, and this type of stretching is called asymmetric stretching. Usually asymmetric stretching, for asymmetric stretching, more IR radiation is absorbed. That is, here you can see 2926 centimeter inverse, whereas in symmetric stretching it is 2853. Okay. In bending vibration, the position of atoms change with respect to their original bond axis. That is, the position of atoms change with respect to their original bond axis. See, these are the bending vibrations. The bending vibrations are of four types: scissoring vibration, wagging, rocking, and twisting. Scissoring, rocking, wagging, and twisting. Scissoring and rocking are in-plane vibration. Scissoring and rocking are in-plane vibration, while wagging and twisting are out-of-plane vibration. In the scissoring vibration, you can see the movement of atoms is in opposite direction with change in their bond axis as well as bond angle. You can see here the position of hydrogen changes. Here changes their bond axis with respect to their bond axis. It is the bond axis, carbon-hydrogen axis. The position of hydrogen changes with respect to this bond axis. Here also the carbon-hydrogen bond axis, the position of hydrogen changes with respect to this bond axis. But these two hydrogens are moving opposite sides, this side and this side, within the plane, and so it is in-plane vibration. Okay. In the rocking vibration, there is also an in-plane vibration. The movement of atoms takes place in the same direction. You can see here the movement of hydrogen atom takes place in the same direction with change in their bond axis. Here the bond axis like the CH axis, here the CH axis, but the movement of atom takes place in the same direction, changing their bond axis, with changing their bond axis. See, all these three atoms are within this plane, and the movement of these hydrogen atoms are in the same direction by changing its original axis, carbon-hydrogen axis. And this type of vibration is called rocking vibration. These two types of vibration, scissoring and rocking, are in-plane bending vibrations. Okay. The remaining two bending vibrations are wagging and twisting. These two are out of plane vibration. Wagging vibration and twisting vibrations are out of plane vibration. In wagging vibration, two atoms simultaneously move above and below the plane with respect to common atom. See, it is the plane with respect to this carbon atom. These two hydrogen atoms move both above the plane of this carbon atom and below the plane of this carbon atom, both above or below with respect to the plane of the carbon atom. And this type of vibration is called wagging vibration. Here both the hydrogen atoms move above the plane of carbon atom or may both move below the plane of this carbon atom. Such a type of bending vibration is called wagging vibration. And in the twisting vibration, that is also an out of plane bending vibration. One of the atom moves up, and the other moves down, with respect to the common plane of carbon atom. That is the plane of carbon atom. With respect to the plane of carbon atom, this hydrogen moves up while this hydrogen atom moves down with respect to this common atom, carbon atom. And this type of vibration is called twisting vibration. Both this wagging and twisting are out of plane vibration, whereas scissoring and rocking are in plane bending vibrations. Okay, we know the lesser energy is required for bending a spring than that required for stretching it. That is, energy needed for bending a spring is lower than that required for stretching it. Analogously, bending vibrations require lesser energy than that for stretching vibration. Okay, thus the absorption band resulting from bending vibration appear at lower wave numbers than those resulting from stretching vibration of the same bond. Stretching vibration usually cause peak of high intensity. You can see these are the bending vibrations in octane, the molecule octane. It is the IR spectra of the molecule octane. Okay, that is C8H18, C8H18 octane. You can see here there are bending vibrations, peak for bending vibrations, that is C single bond H scissoring, C single bond H methyl rocking, long chain methyl rocking, and all these having lower wave numbers compared to stretching vibration. These are carbon hydrogen stretch. That is the peak obtained for carbon hydrogen stretch. It is with a very high intensity compared to these bending vibrations. You know, stretching vibrations usually cause peaks of high intensity. You can see these are intense to peak. Stretching peaks are intense compared to bending peaks. And also bending peaks are usually obtained with lower wave numbers compared to stretching, those required for stretching vibrations. Here it is carbon hydrogen stretch. We will get two peaks, 2971 and 2863, symmetric and asymmetric carbon hydrogen stretching frequencies. Then when we compare with these frequencies, this frequency of vibrations absorbed for bending is very small compared to these vibrations. Okay, in the case of octane molecule. Okay, it may be noted that for various stretching and bending vibration, a bond have a definite and quantized frequency of their own. That is, for stretching and bending vibration, a bond have a definite and quantized frequency of itself. When infrared radiation of the same frequency is incident on the molecule, there is absorption of energy resulting in the increase of amplitude of that particular absorption. Now the molecule is in the excited state. Such an absorption gives rise to a peak in the IR spectrum. That is what is happening after the absorption. Each of the bond will have a quantized frequency of their own as bending and stretching vibrations. When infrared radiations of the same frequency is incident on that molecule, there is absorption of energy resulting in the increase of amplitude of that absorption. Now the molecule is in the excited state. Such an absorption gives rise to a peak in the IR spectrum. That is what is happening. Then what happens when the molecule gets excited? From the excited state, the molecule returns to the ground state by release of this extra energy either through rotational or collision or translational process resulting in the increase of temperature. By this process, that is release of this energy by rotational or by collision or translational process, there will be increase in temperature of the sample under investigation. That is what is happening after the absorption of IR radiation. Okay. See, the IR spectra of polyatomic molecules may exhibit more than one vibrational absorption bands. More than one vibrational absorption band in the case of polyatomic molecules. This number, that is the number of these bands, corresponds to the number of fundamental vibrations in the molecule, which can be calculated from the degrees of freedom of molecule. That is, the number of these bands obtained for these polyatomic molecules corresponds to the number of fundamental vibrations in the molecule, which can be calculated from the degrees of freedom of the molecule. Then the degrees of freedom of a molecule are equal to the total degrees of freedom of its individual atoms, right? Each atom has 3 degrees of freedom corresponding to 3 Cartesian coordinates x, y and z necessary to describe its position relative to other atoms in the molecule. Therefore, a molecule having n number of atoms will have 3n degrees of freedom. In the case of non-linear molecule, 3 of the degrees of freedom describe rotation and 3 describe translation. Thus, the remaining 3n minus 3 minus 3, that is 3 for rotation and 3 for translation, that is equal to 3n minus 6 degrees of freedom are its vibrational degrees of freedom or fundamental vibration. That is, for non-linear molecule, the degrees of freedom that is equivalent to fundamental vibrations is equal to 3n minus 6. Okay. In the case of a linear molecule, only 2 degrees of freedom describe rotation. That is, in the case of linear molecule, only 2 degrees of freedom describe rotation, because rotation about its axis of linearity does not change the position of the atom. That is why the rotational freedom is 2 instead of 3 in non-linear molecule, and 3 describe translation. Thus, the remaining 3n minus 2, that is for rotational freedom, minus 3 for translation, that is equal to 3n minus 5 degrees of freedom or vibrational degrees of freedom or fundamental vibrations for linear molecules. For example, the number of vibrational degrees of freedom for the linear carbon dioxide molecule, carbon dioxide is linear molecule and can be calculated as follows. The number of atom, carbon dioxide having 3 atoms, 1 carbon and 2 oxygen, there are 3 atoms, total degrees of freedom 3 into n, that is equal to 3 into 3, that is equal to 9. Rotational degrees of freedom, being a linear molecule, it is 2. Translational degrees of freedom 3. Therefore, the vibrational degrees of freedom 3n, that is 9 minus 2 minus 3, that is equal to 4. That means, since each vibrational degrees of freedom corresponds to a fundamental vibration and each fundamental vibration corresponds to an absorption band, for carbon dioxide molecule, there should be 4 theoretical fundamental bands. That is, since each vibrational degree of freedom corresponds to fundamental vibration and each fundamental vibration corresponds to absorption band, here there are 4 fundamental vibrations. For carbon monoxide molecule, there should be 4 theoretical fundamental bands for carbon dioxide. Okay. Similarly, for a non-linear molecule, ethane is a non-linear molecule, C2H6. The vibrational degrees of freedom can be calculated as, the total number of atoms are 8, n is equal to 8, 2 plus 6, 8. Total degrees of freedom 3 into n, that is 3 into 8, that is equal to 24. Rotational degrees of freedom, being a non-linear molecule, it will be 3. Translational degrees of freedom also 3. Therefore, vibrational degrees of freedom will be 24. 3n minus 3 minus 3, that is equal to 18. Thus, theoretically, there should be 18 absorption band in the IR spectrum of ethane. Right. But it has been observed that in actual IR spectra, the theoretical number of fundamental bands are seldom obtained because there are certain factors which decrease or increase the number of bands. The following factors decrease the theoretical number of fundamental bands. For example, frequencies of fundamental vibrations which fall outside the region. That is, the frequency of fundamental vibration which fall outside the region. It is the 4000 to 667 centimeter inverse, the IR region. Sometimes the fundamental vibrations fall outside this region. Similarly, fundamental bands which are so weak and they are not observed. If the fundamental bands are so weak, it will not be observed. Similarly, if the fundamental bands which are so close that they coalesce. Another factor is the occurrence of degenerate band from several absorption of the same frequency in highly symmetrical molecule such as carbon dioxide. It is important. The occurrence of degenerate band from several absorptions of the same frequency in highly symmetrical molecules such as carbon dioxide. Similarly, certain fundamental vibration bands which do not appear in the infrared spectrum due to lack of the required change in dipole moment of the molecule that we had already seen. That is, for example, in carbon dioxide molecule. That is, certain fundamental vibration bands which do not appear in the infrared spectrum is due to lack of the required change in dipole moment of the molecule. We had already seen the absorption takes place only when there is a change in dipole moment in the molecule because of the vibration. That is the basic condition for IR absorption. Some of the fundamental vibrational bands will lack the required change in dipole moment in the case of carbon dioxide, for example. Okay, these are the factors that will decrease the theoretical number of fundamental bands. Okay, see, the carbon dioxide molecule is linear and has 4 fundamental vibrations. That is 3 into 3 minus 5. That is equal to 4. Thus, 4 theoretical fundamental bands are expected, but actually carbon dioxide shows only 2 fundamental bands. What is the reason? The symmetrical stretching vibration in carbon dioxide is IR inactive. Symmetrical stretching, it is the dark or shaded ball is carbon and unshaded ball are oxygens. Then you can see it is symmetrical stretching. Both sides have the same atom, oxygen and oxygen. Symmetrical stretching. It is IR inactive because it produces no change in the dipole moment. It produces no change in the dipole moment. The symmetrical stretching of carbon dioxide produce no change in dipole moment, and so it is IR inactive. Okay. Similarly, the 2 bending vibrations are equivalent and absorbs at the same wave number. Here the scissoring, these 2 bending vibrations are equivalent and absorb the same wave number, that is about 667.3, and hence carbon dioxide gives 2 fundamental vibrations only, that is vibrations due to asymmetrical stretching, vibrations due to asymmetrical stretching or fundamental vibration due to asymmetrical stretching, and a bending vibration because these 2 bending vibrations are equivalent, and hence we get only 1 fundamental band for these 2 bending vibrations at around 667.3. See, the asymmetrical stretching vibration occur at 2350 centimeter inverse. 2350 centimeter inverse. And so carbon dioxide, we can say carbon dioxide gives two fundamental bands, one at 2350 centimeter because of the asymmetrical stretching, and the other at 667.3 centimeter inverse for bending vibration. And so two fundamental bands will be obtained in the case of carbon dioxide. Okay. You know, in a molecule having a center of symmetry, the vibrations which are symmetrical about the center of symmetry are inactive. Thus, carbon dioxide, the symmetrical stretching in carbon dioxide molecule is IR inactive because the carbon dioxide molecule has a center of symmetry. Similarly, the symmetrical carbon-carbon double bond stretching vibration in ethylene also IR inactive because it has a center of symmetry, and hence carbon-carbon double bond stretching, symmetrical carbon-carbon double bond stretching is IR inactive. Okay, but ethylene molecule shows CH stretching vibrations. CH stretching vibrations. Ethylene molecule shows CH stretching vibration, but it will not show C double bond C stretching because of the presence of center of symmetry. Okay. Similar to carbon dioxide. Carbon dioxide molecule will not show symmetrical stretching vibration because of the presence of center of symmetry. Similarly, symmetrical diatomic molecules such as H2 molecule. H2 molecule is symmetrical. H single bond H. It is symmetrical. N2 molecule, O2 molecule, and Cl2 molecule. All these are symmetrical diatomic molecules. All these will have center of symmetry and do not absorb IR radiation because they will not change their dipole moment. There is no dipole moment change during the absorption because it is symmetrical and possess a center of symmetry. But unsymmetrical diatomic molecules, you know, like carbon monoxide and iodine monochloride, I single bond Cl, or carbon monoxide, absorb IR radiation. That is important. Okay. You know, the appearance of certain additional bands in addition to fundamental bands, all of which have a very low intensity compared to the fundamental bands, increases the expected theoretical number of fundamental vibrations. They are overtone bands, additional bands or combination bands, subtraction bands, or difference band, difference band, etc. Okay, all these bands have 1/10 to 1/100th the intensity of fundamental bands, right? For example, overtone bands may arise if a molecule is excited. For example, from its first vibrational level to the third vibrational level. First vibrational level to the third vibrational level. The energy required is almost twice of that required for the excitation to the second vibration level. In this way, if there are two fundamental bands, for example, at X and Y centimeter inverse, then the overtone bands can be expected. For example, at 2X, 2Y, 3X, and 3Y. Okay. See, the intensity of overtone decreases as the order of overtone increases. For example, the second overtone, that is 3X or 3Y, is usually less intense than the first overtone 2X or 2Y. Consequently, second and higher overtones are rarely observed, whereas the first overtone are observed only for strong bands. Okay, that means the intensity of overtone decreases as the order of overtone increases. Right. Then if there are two fundamental bands, one at x centimeter inverse and the other at y centimeter inverse, then the combination bands can be expected. For example, at x plus y or x plus 2y or 2x plus y centimeter inverse, etc. That is, if the two fundamental bands at x centimeter inverse and y centimeter inverse, then the combination of these bands can be expected as x plus y centimeter inverse or x plus 2y centimeter inverse and 2x plus y centimeter inverse, etc. Similarly, if there are two fundamental bands, one at x centimeter inverse and the other at y centimeter inverse, then the difference bands can also be expected. For example, at x minus y centimeter inverse or x minus 2y centimeter inverse and 2x minus y centimeter inverse. Right. See, we can calculate the vibrational frequency of bond with reasonable accuracy using Hooke's law. Okay, which correlates frequency with bond strength and atomic masses. According to Hooke's law, the vibrational frequency nu is proportional to square root of bond strength divided by mass. It is otherwise represented as the frequency of vibration or vibrational frequency nu is equal to 1 by 2 pi into k divided by m1 m2 divided by m1 plus m2 all raised to half, where nu is frequency and k is a constant related to the strength of the spring. Here the bond, that is the force constant of the bond, k is represented as the force constant of the bond, and m1 and m2 are the masses of the two balls. Here these are atoms. You know, the bonds are considered as spring and atoms are considered as balls in this system of calculation of vibrational frequency according to Hooke's law. The quantity, m1 by m1 m2 divided by m1 plus m2, often expressed as mu, is called the reduced mass of the system, and hence this equation may be represented as nu is equal to 1 by 4 pi into square root of k by mu, where mu is the reduced mass, that is equal to m1 m2 divided by m1 plus m2. Okay, that is how we can calculate the vibrational frequency using Hooke's law. Okay, according to this equation, the vibrational frequency of bond is expected to increase when the bond strength increases. When the bond strength increases, that means the force constant that is related to bond strength increases, and also when the reduced mass of the system decreases. When the reduced mass of the system decreases or the bond strength increases, then the vibrational frequency of the bond also expected to increase. Thus, we can predict that C double bond C and C double bond O stretching will have higher frequencies than C single bond C and C single bond O stretch respectively, because C double bond C and C double bond O are having higher strength, bond strength than C single bond C and C single bond O stretching respectively. We can also expect to find carbon hydrogen and oxygen hydrogen stretching OH stretching and CH stretching absorption at higher frequencies than carbon single bond carbon and carbon single bond oxygen stretching. Okay, it is because of in carbon and carbon oxygen, their reduced mass is greater than carbon hydrogen and carbon oxygen hydrogen respectively. Okay, that is the reason, right? But without accurate data on force constants, however, some caution should be exercised in predicting the exact trends other than this general way. For example, on the basis of reduced mass, we expect the X single bond H stretch frequencies to fall along these series: CH greater than, NH greater than, OH greater than, FH, because the reduced mass increases along these series. But here you can see carbon, nitrogen, oxygen and fluorine. Their electronegativity continues to increase. Because of the increase in electronegativity, the bond strength or force constant also increases along the series, and hence the force constant factor nullify the reduced mass factor, and hence actually the frequency of vibration increases along this series. Okay, I think you might have got a clear idea about the basic principles underlying in the infrared spectroscopy. In the next or upcoming videos, I will discuss the factors influencing the vibrational frequencies and the applications of infrared spectra in the determination of structure of organic molecules. Thank you for listening. Thank you.